Hello everyone. From now on, let's start presentation of our term project proposal. Our project is on implementation of the RUC attack, which stands for reused unvalidated caches. Our presentation will proceed in the following order. I will cover the team introduction, paper selection, and key contributions. And next, our methodology, requirements, and timeline will be discussed. First of all, let's introduce our team. We have named our team SoS, which stands for Sword of Shield. This name is inspired by the title of our selected paper, Your Shield is My Sword. Our team consists of 4 members. Each member has taken a leading role for this project. The paper we have chosen to re-implement is titled Your Shield is My Sword, a persistent denier of service attack via the reuse of unvalidated caches in DNS SEC validation. This is a very recent and relevant paper presented at the 34th Unix Security Symposium in August 2025. We selected this paper for 3 primary reasons. First, the importance of DNS-SEC. DNS is a core infrastructure of the Internet. Its security extension, DNS-SEC, is now deployed in over 90% of all top-level domains. This implies that a vulnerability in DNS-SEC can cause widespread damage to both general Internet users and corporations. Second, this paper demonstrates a key paradox. The DNS-SNC troubleshooting function can itself cause a persistent denial of service. This paradox, where a security protocol is used as an attack vector, is what sparked our interest. Third, there is a lack of clear standards for caching and reusing the unverified data that comes from troubleshooting. This has led to different implementations and vulnerabilities. This lack of a formal guideline clarifies our project's objective to verify these vulnerabilities and propose more secure policies. Then the paper makes 4 key contributions. First, it proposed a new attack technique called RUC. This is a novel DOS attack that exploits the caching and reuse of unverified data from the DNS-SEC troubleshooting function. Second, it details 3 attack variants. RUC-SEC, which forges DNS key or DS records, and RUC-NSIP, which forges name server IP addresses. RUC-EDNS-0, which manipulates EDNS-0 function support information. Third, it presents large-scale, real-world measurement. The results from Section 6 show that 5 out of 6 tested DNS software and 28 out of 29 public DNS services are vulnerable. Over 65% of the world's open resolvers are affected, and some systems can experience a persistent DOS denial of service for over 24 hours. Finally, the research had significant industry impact. Bind, Cloudflare, and OpenDNS have already applied patches based on the researchers' proposals. As noted in section 7.1, standardization is also in progress through an IETF draft.
Environment and requirement. For this project, we used several tools and technologies. We set up DNS servers, an attacker server, and used Docker to create the resolver and name server containers. The experiment runs on Python 3.1 or higher, and we used DNSLib, a Python library for handling DNS packets. For hardware requirements, we recommend at least 4 CPU cores and 8 GB of RAMs to run the experiment smoothly. Methodology. Let's start with the environment setup. First, we create a virtual network. Then, we launch 3 Docker containers, a resolver container that returns IP address, a name server container that provides the final IPs, and an attacker and client container. All 3 containers are connected to the same vulture network so that they can communicate with each other. Based on this setup, we conduct 3 experiments to reproduce the attacks. Experiment number 1, RUC-SEC attack. This attack targets the DNS-SEC chain, focusing on DNS key and DS records. The attacker sends a checking disabled query so that the resolver accepts responses without validation. By injecting forged DNS key or DS records into the cache, the attacker makes the resolver reuse those unvalidated records later. When a normal unvalidated query arrives, the resolver fails DNSSEC verification and returns serve fail. In this experiment, we observe how this invalidated data stays in the cache and how long the validation failure persists. Experiment 2, RUC and SIP attack. In this experiment, we manipulate the name server's IP address. The attacker poisons the resolver's cache so it believes the name server is at a forged or unreachable IP. When clients send normal queries, the resolver forwards them to the wrong address, leading to timeout or serve fail errors. We also check how quickly the resolver recovers once the forged IP expires or the cache refreshes. Experiment number 3, RUC EDNS 0 attack. Here, the attacker tricks the resolver into thinking that a name server does not support EDNS 0 by removing the OPT records from a response. As a result, the resolver sends the DNS SEC queries without OPT, and the name server responds without RRSig data, causing validation to fail again. Through this experiment, we confirm how the resolver caches EDNS 0 capability and how that affects DNSSEC verification. Mitigation strategies. We propose 2 main mitigation methods to reduce or eliminate the impact of the RUC attacks. First, we shorten the TTL of unvalidated records. By limiting how long forged or unverified data remains in the resolver's cache, we can significantly reduce the duration of the denial of service effect. Even if an attacker successfully injects invalidated records, those records will expire quickly and be replaced with correct data from the authoritative server. This approach acts as a temporary but practical safeguard, helping to contain attackers' impact without requiring major software changes. Second, we use the latest version of DNS tools and resolvers. Updated DNS software such as Bind, PowerDNS, or Unbound has already addressed key issues like the improper reuse of unvalidated data and the excessive caching of eDNS zero capability states. By applying these patches and maintaining up-to-date configurations, we can prevent the root cause of these attackers rather than just limiting their effects. This represents a long-term and more fundamental solutions that improves both DNSSEC reliability and overall network resilience. Together, these two strategies, one short-term and one long-term, aim to make DNS resolvers more robust against RUC-type attacks and maintaining a trustworthy validation process. Project timeline. Our project is planned to take place over 5 weeks. In week 1, we will focus on building the entire experiment environment from the ground up. This includes setting up the Vultr network, creating all the 3 Docker containers, the resolver, name server, and attacker, and making sure that communication between them works smoothly. By the end of this week, we should have a fully functional test bed for the RUC attack experiments. In week 2, we will start running our baseline and RUC-SEC experiments. Here, our goal is to verify that the basic DNSSEC validation process works correctly, and then reproduce the RUC-SEC attack where forged DNS key or DS records are injected into the resolver cache. This rig establishes the foundation for the more advanced attack scenarios that follow. In week 3, we move on to the RUC and SIP and RUC eDNS 0 experiments. We will manipulate the name server IP addresses and the eDNS 0 capability caching behavior to observe how resolvers respond to these attacks. This phase is where we collect most of our performance and failure data. In week 4, we focus on testing mitigating strategies. We plan to adjust TTL values for unvalidated records, upgrading DNS tools to their patched versions, and measure how effectively these mitigations shortened or eliminated the dose effect. This week helps us evaluate both short-term and long-term solutions. Finally, in week 5, we will compile and analyze our results. We will prepare the presentation slides, write the final project reports, and summarize our findings, including which mitigations were most effective and what lessons we learned from the experiment. Thank you for listening.